Hello, today we're going to talk about structure 3.2.8 and 3.2.9. This is an HL only topic, and it's all about mass spectrometry and infrared spectrometry. So let's talk about mass spectroscopy first. And effectively, the first thing that's going to happen is you're going to create a molecular ion. So they're going to take their organic compound that they're going to test and remove an electron. And that generates a cation, which we call the molecular ion. That's important because when you put it into the mass spectrometer, the molecular ion is going to be passed down and around a curve, okay, like this. And it's in like this tube, effectively. And then there's going to be a magnetic field applied at the end and a sensor. Okay, so there's going to be a negative charge and a positive charge like that. And as the positively charged ion, the molecular ion, moves around this corner, it's going to be attracted to that negative side of the electric field. This allows it to be separated by mass because heavier molecules, heavier molecular ions, won't be deflected as much by that magnetic field, whereas really lightweight molecular ions will be deflected a lot. So by the time the different pieces get to the sensor, it'll be separated by mass. And effectively, in this process of creating molecular ions, you're going to make a bunch of different fragments of different sizes. And that's really important because it separates in this mass spectrometer by the mass. So while you don't necessarily have to be able to explain how the mass spectrometer works, you do need to be able to read the fragmentation patterns that arise. And so it will look like a bar graph almost, and you'll have the mass of the fragment on the bottom, but it's typically given as m/z, the mass to charge ratio. But if you've only removed one electron, they're all going to have that same positive charge, so it's effectively just mass. And then there's going to be different masses that show up. So whatever the mass fragments happen to be. Maybe it's like this. I don't know. I'm making up some numbers. It doesn't really matter for this what the masses are yet, because I'm just using this as an illustration. Whatever the biggest one is, this is the molar mass of the full molecule. So effectively, for this one, it has only lost an electron. And electrons do not significantly impact the mass of the overall molecule. So whatever the largest fragment is equivalent to the molecular mass of the compound. So if you have a compound like C6H14, which wouldn't really match up with these masses, but whatever the mass is of this thing, that's going to be the largest mass in your mass spectra. It's just going to be in the form of a molecular ion, so a positively charged ion. Same mass, ionic form. So when you put a whole molecule into the mass spectrometer and it splits up into fragments, there's specific locations where the bonds are likely to break, more likely to break, and so you wind up with very common fragments. And those really common ones are listed in the data booklet in section 22, and they give you the masses of those. And really this is just to save some time. You don't really need this section. It just, again, saves time, because if we look at a CH3 fragment, that's 12 for carbon plus 3 from hydrogen gives us 15. Hey, that's the same. Or oxygen is 16 and hydrogen is 1, that gives us 17. So again, it's just to save you a little bit of time. If you see these numbers, it's likely to be this fragment that's listed. Right? So let's say I've got a molecule like, I'll draw the structure. Let's do this. This is a really simple alcohol. This would be butanol. It's likely to split into fragments like this. So the CH3 fragment, you're probably going to see some of these, you might see some of these, you might see some of these. So anywhere between carbons or between carbon and oxygen, it's likely to break apart. You will also see very frequently where just one hydrogen leaves, but that mass of one doesn't always show up on the spectra itself. So let's put that all together for a mass spectra of a real molecule. So let's say I've got ethanol. And ethanol is CH3, CH2, OH. Okay, actually, let me draw it like this. It's a little clearer. Okay, so if you were to add up the mass of this whole entire thing, the 2 carbons, 1 oxygen, and 6 hydrogens, its mass is 46. So in your mass spectrum, you're going to see a peak at 46, and that corresponds to the C2H6O positive molecular ion. So you just take the whole molecule and change it into a positive ion. We'll also probably see some of the molecule present at 45. One of these hydrogens could come off and leave behind 45 left over as the mass. So that's a possibility. You could also see where this whole CH3 leaves. And if you use your data booklet, you know that CH3 is a mass of 15. And so 46 minus 15, you have 31 left over. So you'll also probably see a fragment at 31. Let me go ahead and label both of these ones. The 45 was just C2H5O plus because it's lost 1 hydrogen. The 31 results when you lose a CH3 group. So you're left with CH3O positive. Remember, they're always molecular ions. You could also have your molecule and lose the OH. Take that off, and you're left with just the C2H5 positive ion. And so OH had a 17, and so it'd be left with a 29 as the mass fragment. And then you could have, again, where this is splitting off, this CH3 group can pop up on the spectra as well at 15. So CH3 plus would be my last molecular ion there. So that's kind of how this works. Usually they'll give you the spectra, and then you have to work backwards to figure out something about the compound, or assign which fragments go with which peak on the graph. But it's easiest if you just draw the full structural formula and split it in places that make sense to get that size fragment. Before we get into infrared spectroscopy, I want to take a second and review a little bit with electromagnetic radiation and wave numbers. Remember, when we're talking about waves, we usually refer to the wavelength, which is the distance between crests. We talk about frequency, F, which is the number of waves that pass a point in a given amount of time. That's usually inverse seconds. Wavelengths usually in meters. That's the number of waves for a given amount of time. And then, of course, we'll use like energy in joules. And the higher the frequency, the higher the energy, and the shorter the wavelength. Now, we also have something called wave number. Wave number is the number of waves that pass a point in 1 centimeter. The number of waves for a centimeter. This is a little different than frequency, which is the number of waves in a certain amount of time. This is the number of waves in 1 centimeter for wave number. So the unit winds up being inverse centimeters instead of inverse seconds. And but it's very closely related to frequency. As wave number increases, frequency is increasing, wavelength is decreasing, energy is increasing. This is also a good time to review the types of electromagnetic radiation and their effects on the atoms. So radio waves can have an effect. They're very low energy, but they can affect things like nuclear spin for certain atoms. We're going to get to that in sections 10 and 11. So radio waves, lowest energy there. The next one up is microwaves. Now microwaves are a little bit higher energy than radio waves, and they can affect the rotation of bonds, bond rotation, typically single bonds, what we're talking about there. The next one up is infrared radiation, a little bit more energy, and that causes bonds to stretch or bend, and sometimes we'll call that vibrations. And the next highest is visible or UV radiation, which can cause electronic transitions. So if there's enough energy, they can cause the electrons to move between energy levels, which results in things like the atomic emission spectrum. You can also use X-rays to figure things out about atoms. It's a little bit outside the scope of this course, but X-ray crystallography can tell you things about bond length or bond angle. It works a little bit differently, but you can think of it like an X-ray is taking a picture of your bones or your teeth, and it's in the same way it kind of takes pictures of the molecules so you can see the structure of molecules. It works a little differently, but same kind of concept, at least in your brain. So since we're talking about infrared radiation, let's get a little bit more specific with the bonds stretching and bending. If you only have one bond in a molecule, so let's say they're two different atoms and this is their bond, the bond can only just stretch. It can extend and get closer together depending on the infrared radiation. It has that certain amount of energy that causes it to stretch. If you have more than two atoms, though, you have a little bit more options. Go like this, and these are my two bonds. And of course, this one I'm showing it kind of bent to illustrate, but this still works with linear molecules. It's just a little harder to draw. So you can have the bonds, the individual bonds stretching. Okay, and they can stretch. They can stretch in the same direction. They can both go out. They can both go in, or they could go in opposite directions. So those are some different options for stretching. So I'm just going to go back to the double so we know that those are just options. But we can also have a bend effect going on because there's two bonds that can, bend relative to one another. And so there's kind of more things going on and more possibilities for the infrared radiation to affect the stretching and bending of those molecules. So the specific type of bond is going to involve infrared radiation with different wave numbers. And remember that wave number, at increasing wave number, you're going to have more energy and more frequency. So this is a nice way to, you can always have reference to this in section 20 in your data booklet. As it goes down, it has more energy. So you can see the infrared radiation that's involved for the spectra. So make sure that you always remember that you have this reference. Okay, so here's what an IR spectra looks like. They're, I think, one of the more difficult ones to read just because it's hard to pinpoint exactly where it's, like what number it's referring to. Fortunately, on your data booklet, they give like a range of values. You can usually find what range fits the best. And then it'll also say whether it's a broad peak or not. Broad just means wide. That would be broad. So now in this case, we've got the C double bond O bond there has a particular wave number involved with its stretching. So it's going to, you can see the peak here. You'll also see some CH bonds. Those are going to stretch as well. And that's going to be a little bit higher in wave number than the C double bond O, which is interesting. All right, so this one's just a little bit more complicated. It's not labeled for us, so we need to be able to figure it out. So we have this structure here. It's an alcohol, and the OH bond in alcohols, using your data booklet, has a peak between 3,200 and 3,600. So that's going to be this one. It also tells us in the data booklet that it's a broad peak. So you see how wide that is. That's going to be the OH bond. The CH bonds that are present always is in between like 2850 to 3090. That's going to be here. Those are CH bonds. And then the only other bond that's present in this molecule is the CO single bond, which is in the like 1050 to 1410 range. So that's going to be this one here, just a little bit over 1,000. You could make an argument that it's one of these ones, but they're not going to ask you to be able to distinguish those from each other. It's basically, the only other one there is the CO bond. That's the most frequent kind of question you're going to get for this, is either figuring out the structure or being able to label each of the peaks with the particular bond that is measured using the data booklet. I just want to take a second and relate this back to greenhouse gases. So the greenhouse gases are in our atmosphere, and the most, I don't want to say important ones, but here some examples of some greenhouse gases are CO2, CH4, NO2, and then we've got some chlorofluorocarbons like CCl-F3 or CH2F, CF3. And these are refrigerants. And when they get into the atmosphere, any of these things in the atmosphere are going to absorb infrared radiation that bounces back off the Earth after being emitted from the sun. So I'm going to draw a very crude drawing. I've got your sun, and we've got Earth, and the radiation comes down, hits Earth, comes back up, and the gas molecules can absorb some of that. Some of it doesn't get absorbed, and some of it leaves, but some of it gets absorbed. And to an extent, that's important because we don't want all of the sun's energy to just leave. We need the Earth to have a certain amount of heat. But if too much of it gets absorbed, then the Earth starts to heat up, and that contributes to global warming. So when we have these artificial greenhouse gases, that can really rapidly increase the amount of warming present because it's absorbing more infrared radiation. And that has to do with the bending and stretching vibrations that we were talking about that's measured in IR spectroscopy. So certain molecules are much more likely to absorb infrared radiation. Others are not very likely to absorb infrared radiation, and some molecules are just extremely stable, so they're going to sit up in the atmosphere for a long time and absorb a ton of infrared radiation, more than we would really want to have. So let's look at a couple example questions. So we've got the empirical formula CH2O, simplified mass spectrum shown below. Deduce the molecular formula and give a possible structure. So empirical formula, if I add up the mass of those things, I get that it's 30 grams per mole. But if I use my mass spectrum, I know that the largest one is always my molecular mass. So that means that since it's twice as big, my formula has to be twice as big. And now that we have the molecular formula, we can try to figure out a possible structural formula. You can, if you want, use these masses and the data booklet. 45 pops up on there. 45 is listed as a COOH. So it's worth your time to see if that's going to work. COOH, that means I have one more carbon and I have 3 more hydrogens. So this does work as a possible structure, but let's see if it fits some of the other values. So if I were to split it here, that goes into 45 and 15. 15 also pops up. And then if I were to do 43, well, let's see where that comes from. If I started with 60 and I got rid of 43, that means I'm left with 17. Well, 17 corresponds to OH, which also works. So this is a good structure for the compound. And so that's how you can use the peaks to very quickly figure out possible structures. Okay, so now I have a couple pairs of bonds. Which one would absorb IR radiation of the shortest wavelength, and explain why. Remember, shortest wavelength is higher energy or higher wave number. And of these two, the C double bond O is going to have the higher wave number, or the shorter wavelength. And a good explanation for that is because it's a double bond. It's going to have a shorter bond. It's going to take more energy to stretch that bond. And similar concept with CCl and CBr. Chlorine has a smaller radius, and so the length of the bond between carbon and chlorine is going to be shorter and require more energy or shorter wavelength to get it to stretch. All right, for this example, we've got 2 compounds with the same molecular formula, and they give you the absorptions that are observed in the IR spectra for the 2 compounds. The big difference is this 3000. That's broad. So you would go to your data table, the data booklet, and there is a peak at about 3000. That's very broad. It's 2500 to 3000, and it says for carboxylic acids. So that's our clue that we're definitely going to make a carboxylic acid out of this. And then the rest of the compound will come off of that carbon. So we've got CH2 and CH3, like this. Which makes sense because then we've got that 1730 range, which is really referencing the C double bond O, this bond right there, whereas the OH bond in here was for the 3000, that was broad. And then the 1230 bond refers to probably the CO single bond. And so that's where you get your bonds there in that formula. For compound B, we've got 2 possible isomers. Draw and name them. And so this time we don't have that 3000, which refers to the OH for carboxylic acids. So we don't have an acid. But we still have the CO double bond, and we still have the CO single bond. So it's probably going to be an ester. So we've got 2 possible esters here. We have this ester and this ester. And this top one would be ethyl methanoate. And the bottom one would be methyl ethanoate. And those are your 2 isomers. So this section links back to structure 2.2. What features of the molecule determine whether it's IR active or not? The biggest thing it's IR active is it's going to cause significant stretching or bending of the bonds. And that involves whether or not that the stretch or the bend is changing the dipole moment significantly. So that's why you'll see like CBr is, when that bends and stretches, that is going to change the dipole moment significantly, but maybe a bromine-bromine single bond because those are evenly distributed, they're not going to, when that one bends and stretches, it's not going to significantly change the dipole moment of that. So you'll be able to see bands in the IR spectra if those stretches change the dipole moment. And this section also links to reactivity 1.3. So we're talking about greenhouse gases in this unit. What properties of a greenhouse gas determine its global warming potential? And we talked about some of those greenhouse gases and how they can absorb infrared radiation and kind of hang on to it, and even keep the heat trapped on Earth, basically. So that's its global warming potential. But the other aspect also is has to do with the stability of the molecule, which is why we're linking this to a reactivity concept. So the longer it sticks around and doesn't like break down or change into other gases, the longer it sticks around, the more it has a global warming potential, because it can continue to have effects on the atmosphere, continue to absorb infrared radiation. So like the length of time that the molecule sticks around in the atmosphere is going to also impact the global warming potential of that molecule.